right, Hawk, we're ready. One and two.
So today's lecture or event is going to be actually very interesting, even though there aren't that many people here. We put in more work to prepare this one than any other course in the history of
They're lost.
So it's going to be 3 parts. One is going to be a general introduction to this topic of data visualization. Then in the second part, we're going to go into depth on a special visualization topic rather than trying to cover a million different topics in breadth. We're going to go into depth onto one topic. And that's actually going to involve you guys taking a test. It's completely voluntary, but you will learn a tremendous amount. And it's not actually assessed. This is like you don't really, well, I guess we do assess it, but it's not assessed in the traditional sense, like you don't get a distinction or whatever. But we can obviously share the results. We'll share the results with you to see how you did, obviously. But it's actually for research purposes. So we're gonna test out 2 slightly different teaching methods, and then give 2 tests to see if there's some difference, if that makes any sense. And then that's part. So part 2, you'll learn quite a lot, and then in part 3, we'll use a special piece of software called Tableau, where you're creating something. You're creating visual designs, and you're learning a new tool. So it's sort of like a ramp from pure theory to pure application with 2 transitions in between. Does that sound very exciting? It is. It's going to be really exciting. But before I do that, it would be good just to have everybody's consent. Everything is obviously very voluntary, if that makes any sense. Something could be very voluntary or not. Okay, and since it is a small audience, I will probably try to use your names. Yeah. Maybe we can start out by you guys telling us something, like who you are, where you work, and why you're here, why you're interested in this topic. Shall we try that? Yeah? Anyone want to volunteer to go first? Okay, oh, that's a fun name. The Greek name.
Yeah, that's me.
Stavros?
Yes.
Okay, what like, where do you work?
So I work with the Swansea Employability Academy, and I run social media, I create content for them, do a bit of work on Photoshop, and we interview students that have completed placements. So a lot of like stats come in about students from COA, students from Human and Health Sciences, and I think it would be a necessity to visualize the data and make like infographics as well. So that's my expectation from this, maybe just to understand the numbers that would go into infographic a bit more.
Okay, cool. Psiphon, is that right?
Yeah, I do exactly what he does.
Okay, so you guys know each other.
Yes.
Yeah.
Yes, okay, that's an easy answer. And Haley or Hallie?
I'm Haley.
Haley.
I basically do the same thing, but for the College of Engineering. So
Okay.
we collect a lot of student feedback and then we report it both to the students and also to staff in different ways.
Okay.
So it's just looking at how to make the data easier to digest and more meaningful at a glance, because no one is spending a lot of time looking, in detail at spreadsheets.
Okay, good, good. Maybe we can help with that, maybe not. So I'm going to start with a little kind of psychic reading exercise. I like to practice my psychic powers. And this is a diagram of a thought process that's happening inside your head. You might know it, you might not realize it, you might be fully realizing it, but this is something that, as a society, a pattern of thought and learning that we're all going through. And it starts with a real-world challenge. Now, the three of you guys just explained a real-world challenge that you're facing. You're collecting data, and you're trying to then process it. So you have a real-world challenge. That could be trying to understand thousands of student feedbacks. That could be trying to understand how to build a car. It could be trying to understand the behavior of deep-sea wildlife. It doesn't matter what it is, but we all have these real-world challenges that we're trying to face. It's usually not necessarily constructing something in our daily lives. It's usually trying to obtain a new level of understanding. That's usually what we're trying to do. We're trying to learn something and understand something better than we previously did. Now, all those challenges have some physical or analog approach to increase understanding or to reach a goal. For example, in the student surveys, a physical approach to the student survey problem would be to actually talk to every single student and try to get their feedback on a one-by-one basis. A physical approach to watching deep-sea wildlife would be to get in a submarine and try to follow some tortoise around. It sounds funny, as it is. A physical approach, we could actually build a car. We theoretically could build a car, right? Because we drive a car, we know that somebody builds them, so they do get built. So for every real-world challenge, there is a physical solution that we already know about. However, those physical solutions are usually not feasible, right? It's very difficult for a person to interview 1,000 or 10,000 students to get their feedback, for example. It is physically impossible to get in a submarine and observe deep-sea wildlife over the course of hours or days. It's just not possible. It is theoretically possible to build a car or build a house. Building a house is probably a better example. But we don't have the time, money, and resources to do that, generally speaking. So we're all very familiar with this path, right? These three stages of knowledge evolution. And then there's a dashed line on the two halves of this diagram. This is sort of the real physical world that we interact with. This is the digital world. So we jump from the physical world to the digital world. And instead of trying to build physical or real world solutions to address our challenges, we build digital solutions. So in the case of student feedback, we ask every student to fill out a digital survey, and then we collect data. For the case of deep-sea wildlife, anybody ever heard of the study of deep-sea wildlife in Swansea University? Happens to be a specialty of Swansea University. they attach little sensor devices to all the deep sea wildlife. So they catch a turtle or a cormorant or a penguin, attach a little sensor, let it go, collect data for a few days, and then recapture the sensor and then study the data to try to understand the animal behavior. For building things like cars or houses or buildings or libraries, that's all done in software before it's done in the real world. So digital versions of all the things we make are constructed before the physical versions. And we're used to this pattern of thought. We think, oh, we can't do that in the real world. There must be a software app that does that or can help me do that. But those digital solutions bring a new challenge with them, and that is data chaos. So all the digital solutions we create to all our problems generates data chaos. So very large, complicated, high-dimensional, time-dependent data sets that we don't really understand. Or we kind of know, I'm not getting the value out of this data that I could be getting. I'm not extracting the knowledge that I could and the information that I could be. This is something I call data chaos, and that's the reason why the three of you are here, actually. You have this data chaos problem. And the solution to the data chaos problem is visualization, obviously. If you can see it, then it makes sense, you know. You can understand it. If you can't see it, it's very difficult to understand. You can practice your psychic powers, but it's better, that's not as reliable as using data visualization to study the data. I call that the visualization cosmos. So making order out of the chaos. That's really what the cosmos is. And this diagram is not perfect, by the way. There could be another arrow. Usually what happens is after you visualize your data, you make some decisions, or you're more informed. Ultimately, you want to make decisions. And then this arrow, there could be an arrow that goes back to the real world challenge. So now you're more well informed about your real world challenge, and you can make decisions and iterate through the process over and over again, actually. That's what happens a lot. And this is happening everywhere. Like this pattern, it doesn't really matter where you look, who you talk to, where you are. This is a pattern, a ubiquitous pattern. So in the engineering department, you have these computational fluid dynamics. You might be familiar with that, Haley. You're in engineering, yeah?
I'm not an engineer, but I am in the College of Engineering.
Okay.
Yeah, they do simulations for everything. They have Gravity Sketch for vehicle design and testing. So, you know, things like that. The flight simulator
Exactly.
for aerospace engineering.
You have everything going on there, lots of simulation.
The chemical engineering doesn't have as much, but they're developing that currently.
The Bloodhound is a high-profile one.
That is.
The marine turbine simulation is another high-profile. So CFD engineers generate endless amounts of data. Physicists and astronomers, we often have people studying physics here, generating massive amount of experimental data or image data like satellite data. Sometimes we have marine biologists and biochemists here using these little digital sensors to collect massive amounts of data. Psychologists, sociologists, and criminologists. Had anybody ever heard of EEG before? Those are those sensor devices that they attach to scalps and try to understand brain activity. They don't really work, but they do exist. Surveys are used a lot, right? Surveys are a massive source of data. Sports scientists study videos and events. journalists and the arts and humanities study text. Text is data in the world, that the way I look at the world. A library is a data set. Governments and councils collect the data about everybody that lives here and the resources that they allocate and use and so on. These are just some examples on a professional level on the left-hand side. There are different kinds of professions and where people are collecting and archiving data full time. On the right-hand side are just some examples that are on a more personal level, on a more individual level rather than collective level. So, for example, every bank transaction that you make is stored in a database, at least one database. Every phone call you make is stored in a database. Every time you go shopping, right, there are multiple sources of data.
Send you an email about that.
Every time you pull up a web browser on your phone or on a desktop or a laptop, that data is logged, which website you visited, when you visited, from where you were sitting, what your IP address is, and so on. Every time you get on transport, right, that data is recorded. Every time you visit a doctor, right, you want that data to be recorded. You collect data yourself, you collect photos, and so on. So this is really, this data collection process, the data chaos, is really ubiquitous. It's everywhere and everyone. And I think that it is just a kind of human nature. People like to just collect things, even though they don't necessarily need to collect things. I think it's like a historic survival artifact. I think that's what it is. Now, what is visualization? Are there any questions or comments so far? If you guys have any questions or comments at any time, just interrupt. It doesn't matter. So, visualization has different strengths and different advantages. One advantage is exploration. That's if you have a data set and you don't understand it and you just want to explore it, look for trends, patterns, outliers, and different kinds of characteristics. There's the analysis aspect, and that is if you already are an expert on your data, maybe you're the person that collected it in the first place, and you already have specific questions or hypotheses that you want to answer, or hypotheses you want to confirm or refute. Data visualization is good for presentation, so that's after you've done your exploration and analysis and you want to communicate the results to a wider audience. It's very good for that. Two less obvious advantages that data visualization provides are acceleration and increasing confidence. What do we mean by acceleration? Well, if you think about it, what do we do with data? There is one word that describes what we do with data: all data. Anybody know the word? Anybody feeling psychic? You can sum it up in one word: search. That's what we do. It doesn't matter who we are, what data set it is, we're searching. So data viz accelerates the search process. That's one of its advantages. You might find a trend or a feature in your data set in a few seconds that could have taken months without data viz, if you were just trying to read numbers, for example. So it accelerates the search process by several orders of magnitude, and sometimes it enables a search process that is impossible otherwise. And in the third hour, by the way, we'll see an example of that. It also increases confidence. So as soon as people can see the data that they're collecting, they are more confident that what they're doing is either correct or incorrect. Because what happens a lot of times is people collect data systematically wrong. Like they're making a systematic error in the data collection process. And that pops out immediately as soon as you start generating pictures from it. And so that informs the data collection process and corrects it, and therefore confidence is increased. It can also provide confirmation that what you're doing is correct, and that also increases confidence. So these are 5 nice advantages of data viz. So we have lots of different examples of data viz in action. We can't go through all of them, but I thought I would pick an example to go through in detail for you guys. Maybe what I can do is just summarize each of these very, very briefly, and then I'll ask you guys to choose an example that you think might be interesting to look at in more detail. Does that sound reasonable? So this one is from Physics in Foam Simulation. So it's very surprising, but there is a community that studies the properties of foam, and it's very important actually. So anybody know what foam is used for, a common application of foam?
Insulation.
Insulation, yes. Yes. Anything else?
Packaging.
Packaging, yep. Cleaning agents. You wash your hands probably every day, or maybe take a shower. It's also used for mineral separation, so when we extract minerals from the earth, it's used to separate the minerals from the non-minerals. And it's shocking. Something like 5% of all the Earth's energy is used just for mineral separation. So it's a shocking application actually, with dramatic consequences. Anyways, we have studied we have an example for foam simulation and visualization, so the visualization of foam and its behavior. We have the marine biology, the deep sea wildlife example. So this is from the bioscience department here at Swansea University, where they attached the digital tracking devices to deep sea wildlife and then try to understand what the animal did underwater. You can imagine that's quite challenging. And so they collect lots and lots of data, and they asked us if we could help them understand that data with visualization. Here's a very real-world, down-to-earth example, so to speak. Call centers, understanding call centers and their customers. So we work with a company called QPC, and they write database software that records every event in a call center. And there are lots of events in call centers, especially when you have thousands of agents and tens of thousands, actually hundreds of thousands of calls in this example. So how do you understand the data inside of a call center and the events that take place there? That's one of our examples. We have a sports science example. Rugby is very popular in Wales, the Welsh Rugby Union. And traditionally what they do to study their games and their events is they watch videos. And you can imagine that that's very time consuming, right? To get out a notebook, press play, and then start watching a game to analyze it. That's not very scalable, right? How many games can you watch? And how many notes can you take on each game? And how do you find patterns between games very, very challenging. So we worked on some visualization to help them with that. We have visualization of population healthcare data as one of our examples. So, as you know, the NHS collects the data about all of our health, and they anonymize the data and they release it to the public. So we can study patterns and look for patterns and trends in healthcare in the general populace with that data set. We have a computational biology example. These are scientists that use simulation to study the behavior of atoms and molecules at the molecular level. That is a very, very big active area of research. We have one from engineering, the study of fluid flow through a cooling jacket. Anybody here drive a car? Nobody drives a car here? Oh, that's good. That's quite good. Anyway, if you did drive a car, well, it doesn't really matter. Every car has a cooling jacket, and that prevents the engine from overheating. So we have an example that studies the fluid flow inside of a cooling jacket. We also have one that from engineering again that studies the combustion process inside an engine, a motor vehicle engine. So you all know that cars are propelled by combustion, the process of combustion and mixing oxygen with fuel and watching it explode. And then we have a general flow visualization example. It's called texture-based flow visualization. This is the flow of blood on the surface of an aneurysm. And this is the flow of fuel or through a fictitious or a synthetic geometry. So we cannot go into all those examples because there are too many. But we could choose one and look at it so you guys can see an example of data viz sort of applied to a problem or a challenge. Any opinions about which?
I think either the healthcare data or the business call center data would be more appropriate for us.
Okay.
I'm assuming that you deal more with sort of metrics, so that would probably be the healthcare, but I'm actually dealing with sort of comments. So sort of not verbal, but text, people writing out comments, and so that might be more like the call center. How do you pick out keywords or process that data and make it more, see what's happening and without going through everything manually. So one of those two.
Stavros, what do you think? Which example?
No, I agree with Hayley because originally our job was to call graduates for the daily survey.
Okay.
That was what our job was to basically, and then collate all that data and then pass it on for the big numbers basically. So maybe, as you said, just understanding keywords and in that mass of thousands of students that we were calling, which is being done externally as of now, but still we have to do a pick up on the numbers that come up. So I think I agree.
In the call center.
Okay, good. Psiphon, do you have any?
I agree. That's it.
Yeah. Good. Okay, so let's look at the call center example. But before we do that, I just want to... I have different call center examples, and I thought it might be fun to use an example that is more up to date than what is on this slide. So just a little introduction to the problem. The company that develops the software that collects all the events, QPC, their database stores a lot of information. So you've all called call centers before, yeah. And much to our delight. So what does the database records? It records the number that is calling, when the person called. It also every call starts out in something called an IVR, which is the interactive voice recording system. That's like, hello, you have reached blah blah blah. Press 1 if you want to kill yourself. So it records all of the events, how long you spend in the IVR, which options you choose. And then you're typically put on hold after you make your IVR choices. And then if you're very lucky, you speak to an agent after waiting. That's kind of a summary that most of those phone calls follow this kind of 3-stage-ish process. And if you're lucky, you reach an agent. Sometimes after you reach one agent, you get connected to another agent, and so on. So the question is, how can we visualize that behavior when you have a call center with thousands of agents and hundreds of thousands of calls? So a typical call center might get, for example, 200,000 calls in a day. Can you visualize 200,000 calls? Is there a way to do that? Or what about looking at the behavior of customers and their calls over the time span of a month, for example? Is that possible? So we'll show an example. Let's see. This is the DataViz YouTube channel, by the way. So this topic has its own YouTube channel. And there are lots and lots of examples here. And I'm going to try to find one of the call center examples. This is one of the call center examples. I think I'm going to do look at a different one, if I can find it. There's another call center example. Let me see. River State, that's the one I'm looking for. River State. Where is the River State example? Okay, did I forget to upload that one? Maybe I forgot to upload that one. meantime, I will just make sure it's not already uploaded. Ah, there it is.
Seven primary states a caller can exist in. The IVR is an automatic voice
So these are the different states that the typical call goes through that I mentioned: the IVR, the agent, the queue, and the hold. So the hold is when an agent puts you on hold, right? You talk to an agent and you ask a question. Of course, they don't know the answer, so they put you on hold again. And that's just explaining. We also have more properties of calls. For example, when an agent puts you on hold, that's called they make a consult call. So they're consulting somebody else, typically another agent. And there are different kinds of consult calls, inbound consult calls and outbound consult calls. And of course there's the hang-up state. And one of the things that QPC is very interested in seeing is when do people hang up before their call problems are resolved. So this is a visual layout of 250,000 calls over a day. So how is it organized? The events are organized in two ways. They're organized from left to right. So here you can see an IVR event, all the calls here that start out in the IVR. And then they transition to the next state. So here we see a set of calls that starts in an IVR and they actually get transitioned, they get passed to another IVR actually. And then we can see the majority of calls after they go through an IVR state pass through the queue state. Those are all a queue transition. There are a few calls, not very many, that go from the IVR just to the agent. Very, you can see that's very unusual because there's only one thin line. So the thickness of these lines represents the volume of calls. So we see the largest volume transitions from the IVR to the queue, and this very few transition from the IVR to an agent. There are some calls that skip the IVR and start at the queue, and then immediately hang up, which is, these are the kinds of calls that the call center is trying to avoid. They don't want people to call and then hang up before they talk to an agent, theoretically speaking. So that's how to interpret that diagram. The lines show, the curves show the transitions from one state to another, and then the thickness indicates the volume of those calls that makes that transition. You can see here, this is a call end. Now this transition is that those customers that hang up and call again. So that's a bad, that's a set of calls that the call center is trying to avoid. And then you can see the full set of transitions from one state to another. And there are several user adjustable parameters. For example, the thickness of the transitions. The color mapping is also modifiable. So what color is mapped to. And you can see, you can scroll and interact with the visualization. You can scroll from left to right to see. These are also frequency indicators, so the volume of calls. We can apply something called brushing. Brushing is a fancy word for selection, so subset selection. You have an overview, and you might want to select subsets of that overview. And this is the user selecting different subsets of the data. For example, they may want to see a specific set of calls that go through a specific set of states, so they can click on those states and focus on that specific subset of calls. Here is the user focusing on adjusting the length of calls, so they're filtering out different calls. That one is the IVR duration, so filtering out all the calls that only stayed in the IVR for a few seconds, for example. And then watching what happens to the river metaphor after that filtering process is applied. So we start with an overview typically, then we have filtering options, and then we provide so-called details on demand. And when the user wants to see more details, they can hover their mouse over any state and get more details. I'll pause that so we can see. So the user clicked on a state, and then they actually see more details about the calls in that state. For example, there are 17 calls that coming from the IVR, and then 57,000 calls that are coming from the queue. Right, so they see the details, the exact, not the actual data that represents the transitions there. And then 17 calls come in from an agent and zero transition out, which is a good thing, right? And out of the 57,000 calls that come in from the queue, 137 transition out, right? And there are no incoming calls in this example from agents and so on. But anyways, this transition represents 57,000 calls. So that's a very popular transition. This is showing examples of going backwards. So if we want to find out where the calls came from, where they started, we can click on the node in the graph and it traces backwards to find out where they originated from. And most of our interactive visual designs feature different kinds of color maps. And usually we can modify the properties of those color maps. So there are different kinds of color maps available. And some people might find different kinds of color maps more suitable than others for their purposes. This is the user focusing on one special kind of case. So we can see, for example, the pattern of users that hang up and then call back. You can see this cyclical pattern over and over again. There are some cyclical patterns that occur over and over again. But we can always see that the number of the customers that actually calls back after they hang up is much less than the ones that started. So these are very persistent callers. So that red bar represents all lost customers, essentially. the kind of customers that the call center is trying to avoid, so to speak, or the kind of behavior that the call center is trying to avoid. This is an example that's trying to show the average customer journey through the call center. What do most customers experience when they call the call center? You can see some weird calls too, like ones that start in the queue and then immediately hang up. That's very strange. One of the properties of calls that the call center study is something called Net Promoter Score. And I don't know if you've ever called a call center but then received a text message that said, tell us how you found the experience of phoning us. So a little post-call center survey. So they study the results of those post-call center surveys, and they call that the Net Promoter Score. So a high Net Promoter Score indicates that you're very happy with your call center experience, and a low Net Promoter Score means you're not very happy with your call center experience. So they like to study what influences the Net Promoter Score the most. And so one of the theories is that if the interaction with the agent is too short, say it's only 5 seconds, then the Net Promoter Score will be very low. Like somebody talked to an agent for 5 seconds, probably they didn't get their problem resolved, and then that leads to a low Net Promoter Score. And so the user is filtering different options to see, okay, is the amount of time that a caller spends in the queue related to Net Promoter Score? What effect does that have on Net Promoter Score? And also the number of agents they talk to. Like the more agents you talk to, probably the lower your Net Promoter Score will be. Any questions about that example? Okay, and then the other example was related to the healthcare. But that is a good transition into the next part 2 of today's lesson. So instead of trying to study lots and lots of visualization topics, we're going to zoom in and go into depth on a special topic. And this is the topic you're actually going to be tested on. Yeah. And it's related to the healthcare example. So there, it's all connected. Okay, where is the healthcare example? So, the topic is an introduction to tree maps. Has anyone here ever heard of a tree map before? Good? So you're going to learn a lot. You're going to learn a lot now. So a tree map is a special kind of information visualization technique, and it applies to large, very large hierarchical data sets. Anybody know where you would see hierarchical data sets typically? Any ideas? Hierarchical data, does that mean anything to anybody?
Where there are correlations between data sets but don't necessarily apply to all of them.
Mm-hmm. Mm-hmm.
I've seen something called tree maps for probability, so it's tracking events, probability of combined events.
Okay. Well, one example you can think of, can you think of any examples of hierarchies just in general? Like, not necessarily hierarchical data sets, but just hierarchies.
Organizational structures.
Organizational structures, exactly, like management hierarchies, for example. A very common hierarchical data set is one on your phone or on your laptop or on your desktop PC. All of your files are organized into a hierarchy. You have My Computer at the top of the hierarchy, and then there you have different folders, and inside each folder is a set of folders and files. That's a hierarchical data set, right? Very common that you interact with every day. Any data set, any normal data set can be decomposed into a hierarchy. So for example, surveys, you would break those surveys up into different hierarchical categories. One example could be you would break them up by gender. So you start with everybody, then you subdivide into gender, then you might subdivide again into undergraduate versus postgraduate. You might subdivide into first year, second year, third year undergraduate, first year, second year, third year postgraduates. So you'd form a hierarchical structure of your survey data depending on who took it, for example. There are many different ways you could formulate that hierarchy. But you could take any data set, put it into different groups and formulate a hierarchy out of it. And tree maps are a way to visualize very large hierarchical data sets. And here's the idea. It starts with the root of the hierarchy. This is a traditional tree data structure or data set, right? This is hierarchical data, and this is what we're used to looking at. Has everybody seen a tree kind of structure before? So we have the root node of the tree, and then we have that root node of the tree in the tree map. This is the tree map equivalent of this tree, this traditional tree structure. So the root node gets mapped to the large rectangle. And that root node is subdivided into 1, 2, 3, 4 different rectangles on the tree map. This is a leaf node. So these are leaf nodes, meaning they have no children. And these are internal nodes, meaning they have children. So this leaf node, which is a 12, will get mapped to this rectangle in the tree map. Does everybody see that? And this leaf node gets mapped to this rectangle in the tree map view. This internal node gets mapped to this rectangle in the tree map view. And the internal node gets subdivided into 1, 2, 3, 4, 5 leaf nodes. Here they are, 1, 2, 3, 4, 5 leaf nodes in the tree map view. Here we have another internal node. It is mapped to this rectangle here. And it is subdivided. It's subdivided into another rectangle, which is here. So they're really nested rectangles. Does everybody see that? They're nested rectangles. That rectangle is subdivided into 3 leaf nodes, 6, 8, and 11, 6, 8, and 11. Here's a leaf node that's mapped to this rectangle of 5, and then the last one, which is mapped to a rectangle of size 40. So the traditional tree structure is mapped to a set of nested rectangles in the tree map.
It adds up to 100.
That's right, that's right. It doesn't have to add up to 100, but it can add up to 100. And one thing to notice is the 40, this is the largest data value stored at the leaf nodes. It's mapped to the biggest rectangle. So the size of the rectangles represents the amount of data or the data value that they are mapped to. So a small one, for example 1, is mapped to the smallest rectangle. And a 40 is mapped to the largest rectangle, and then you have everything in between. That makes sense, hopefully. Here's another example. In this example, we cannot see explicit internal nodes. I know what the internal nodes are because I understand tree maps. But the internal nodes are not made explicit here. We see explicitly the leaf nodes. Here's another example that shows the internal nodes explicitly. So we start with the root node, which is A162, and that's the big rectangle on the outside. Now A162 is subdivided into three more rectangles. B10, which is a leaf node, that's here. C30 is also a leaf node, and that's here. But now, because there's some padding between there's a little bit of space between the leaf nodes and their parents, we can actually see the explicit internal nodes. D62 is this one here. Right, and there's padding. E60 is an internal node, and it's here. D62 is subdivided into 4 children. F6, G6, H6, I44 is an internal node. And there it is. And then I44 is further subdivided, so we call it a recursive subdivision. Does everybody see that? Here's another example. This is, anybody want to guess what that is?
Motherboard.
A motherboard is, it does look like a motherboard actually.
That's like a computer usage map.
It is a map of your file system, of all of your files. So every single file on the disk is mapped to a rectangle. And they're nested, so you can actually see folders in here. For example, here is a folder, and it contains all the files that are inside the folder. Here's another folder. The folders are indicated by the shading. Here's another folder full of files. This is, has anybody ever had the problem that they run out of disk space? You want to free up disk space? Well, here you can get an overview of the files and their sizes in just 1 second. So if I said, where's your biggest file, and you want to delete that to start with, you could find your biggest file in a fraction of a second on this, by using this visualization. Remember, we said it's usually a search. We're usually searching for something. And DataViz is good at accelerating the search. Well, here we can find the biggest files in fractions of a second. Whereas otherwise, how would you do it otherwise? Anybody ever try to?
Look at actual sizes.
You do it manually, yeah. You'd search manually, clicking on files, looking at the actual sizes and so on. So what are these good for? Basically, they take the existing space, like in this example, and they fill it up right? So we call them space filling. They represent hierarchies. You can actually move up and down the hierarchies interactively. They can represent multivariate data. In this case, the color represents different kinds of files, like user-generated files, program-generated files, operating system-generated files, music files, those sorts of things. They also apply to very large data sets. So I can see thousands of files sitting on my hard drive, in a second. They don't encode any geospatial information, and they don't preserve neighborhoods. That's not very important.